Okay, this should finish up the ideas related to homeostasis that we talked about today in class in your notes. So make sure that you have your notes. Go to the section where you see this diagram. It looks a little different up here, and I'll explain that in just a second. So coming off of the heels of the idea that we can grow bone, right? So we know that we, as embryos, have laid down bone within cartilage to develop a skeletal system. We know that as we age, we grow bone to support our muscle mass. And we also know that anytime we break a bone, damage a bone, that bone can heal itself. And so this section of notes sort of introduces us to the idea of how that could possibly even happen. And so the short answer is we do all of that stuff related to bone growth and development and repair by regulating calcium. So our first little bullet here says we regulate calcium deposition and resorption. Remember, that is the laying down of calcium within the bone and then degrading the calcium out of the bone. And in doing that, we need to look at this feedback loop. So this particular feedback loop is how we adjust calcium in our blood, and sort of what happens if it gets too high and what happens if it gets too low. So a quick reminder on these feedback loops. We looked at them at the very beginning of the year. But right here in the middle, this is a negative feedback loop, which means there is a, quote, normal level homeostasis for calcium. In this case, calcium homeostasis, nice and balanced right here in the middle of the diagram, is between 9 and 11 milligrams per 100 milliliters of blood. So that's what the units back here really mean. So if this is normal and balanced in homeostasis, then to read this loop, if blood calcium levels rise, we look at what happens when the scale is tipped up, and we take this pathway right here to rebalance it. If blood calcium levels decline, we look at what happens when the scale tips down, and we take this loop down here to correct it and bring it back to normal. So this is a negative feedback loop where we have a normal set point, and if we move outside of that sort of normal balanced level, we need to kick something into gear in our bodies to correct it. So in this case, it's important to notice what homeostasis is for blood calcium. We also need to notice the organs and the glands involved in detecting changes, and also I would extend that into releasing hormones. So these organs and glands can release hormones that will stimulate a process that returns us back to normal. So as we go through the next couple of slides and we talk about what happens when calcium levels rise, what happens when calcium levels decline in the blood, we're going to see organs and glands that detect a change. And then we're going to see organs and glands that release hormones that are going to do something that brings us back into homeostasis. All right, so let's take the top loop first. So what happens if calcium in your blood is high? It's higher than the sort of highest level here of the normal range, 11 milligrams per 100 milliliter. Well, the first thing to notice is that the thyroid gland is what is at play right here. So the thyroid gland will detect elevated blood calcium levels, and that gland will also release a hormone called calcitonin. And so the original diagram in your notes, in my opinion, is overly complicated, attempting to show a balance between PTH, this other hormone, and calcitonin. For our purpose, I would cross out that top section of your loop and just write what I have added here, because it's nice and clear and simple. When the thyroid gland detects elevated blood calcium, it releases calcitonin. Calcitonin then is responsible for increasing our osteoblast activity. And so the diagram doesn't entirely say that. It says calcitonin stimulates calcium salts deposition into bone. But remember, that is the activity of the osteoblast. These are our builder cells. And so these blasts will take calcium out of the blood and store it away in bone. That's going to do two things for us. First, it reduces that high blood calcium level, which was the whole point of this feedback loop, right? That's where we started. Blood calcium was too high. And so we take calcium out of the blood, it reduces our blood calcium level back down to the normal homeostasis balanced level that we find right here in the middle of the chart. That's also in the process going to build bone, which is how blasts do what they do. Okay, so if calcium levels are high, thyroid gland is in play, calcitonin is the primary hormone that triggers blast cell activity. Bone is built by taking calcium out of the blood and storing it away in bone tissue. If we look at the bottom loop, if calcium is too low, so there's a different gland. This one is called the parathyroid gland, and actually it's a collection of 4 glands, and it's on the back of the thyroid. So if you take this gland right here and you turn it around, you're going to see these 4 little dots. Those are parathyroid glands. So that is what detects low levels of blood calcium and also what is going to release the hormone needed here. So this shouldn't come as a terrible surprise. The parathyroid releases parathyroid hormone, PTH. PTH will increase the other cell type that we've talked about often, the osteoclast. And so think about osteoclasts. These are our breakdown cells. So they are going to take calcium out of the bone by breaking down the bone, and that will release it into the blood. That's going to do 2 things. That's going to increase blood calcium levels, which was the problem that started this whole lower loop in the first place. And it's also going to be a mechanism for sort of degrading bone. It's harvesting that stored calcium from your bone, which in a normal controlled loop is perfectly fine. If you are harvesting calcium out of your bone more than you are storing it, if that process is an imbalance, then you get to talk about things like osteoporosis and osteopenia, which we're going to do a disease thing. And so I'll leave that kind of looming out there. Now, PTH also does something else. And so connected to calcium levels, PTH can work in your kidneys. And so I think it's pretty cool to sort of sidestep. In addition to what PTH does for osteoclasts, PTH will also go to your kidneys and do 2 things. First, it stops your kidneys from urinating out calcium. It says, hold on to the calcium because calcium is low in our blood. We need to conserve and save calcium. This is called renal retention. If we get to the urinary system this year, we'll talk more about renal retention. PTH also tells the kidney to increase vitamin D production. And so that's a little more complicated path. Vitamin D is going to do several things. And some of you are probably going, wait a minute, I thought our skin made vitamin D. Well, check out this diagram right here. You do use sunlight to create vitamin D, a version of vitamin D in your skin. You also can eat it. So it comes in the food. That heads to your liver and gets converted into a different form of vitamin D, which heads to your kidney to be converted into a final form of vitamin D that is usable by these organs and organ systems. So focus right here on our intestines. If PTH tells our kidney to amp up this vitamin D production or synthesis, that is helpful when it acts on our intestines. So it's going to go to our intestines and it's going to make it much, much easier to absorb calcium out of the food that we have eaten. And so keep in mind, PTH is stimulated when blood calcium levels are low. So all of the effects of PTH here, both on osteoclast activity and on the kidneys, are going to work towards saving, harvesting, collecting more calcium to boost that low blood level that started the release of PTH in the first place. All right, so the next time we kind of chat, we're going to look at different diseases that are impacted by genetics, but also by misregulation or dysregulation of this feedback loop. Okay, you guys are done.